Hello there. This video is going to talk about how to perform a hammer test on an article. And we're going to talk about setting up the frequency resolution, windowing, how you do that um, for a test where we want damping or we want to know the mode shapes of a structure accurately. So our test article here is a blade from a JT8D, I think it is, turbine engine. So a jet engine blade. It's hanging from bungee cords. We have one accelerometer on the end. Tape the cable down to try to keep from getting too much extra damping from the cable, slapping around. And then we're using an impact hammer to excite this. So before we start, let's just talk about impact hammer technique. So we call this a hammer, but we don't swing it like a hammer. It's really more of a flick. So whenever you're hitting the structure, what you want to think about, what I like to think about is line up the hammer so that it's perpendicular to the surface so that all the force goes in the intended direction. And then just do a little pull back and tap. And so just a little flick like that. And then you also have to pull the hammer out of the way so that you don't get a double hit. If I kept it in here, it'd keep hitting over and over again. But yeah, so when we want a hammer hit, it's really just a flick of the wrist there. And the alignment is what lets you keep the hammer perpendicular to the surface so that as we go to other points, we can always have the measurement be in the intended direction. All right. So that's what a hammer hit looks like. I guess let's do one right here too, just so you can see. There, it's very stiff. You don't hear it resonate at all. Where down there, you can hear it ringing just a little. Okay, so that's the technique. Let me share the screen and let's look at settings in Siemens TestLab. So I've skipped over all the channel setup, everything else. The first thing you see in Siemens is the impact scope where you can set the level. You want to use up all available range for the hammer and for the accelerometer. I'm going to turn the hammer down just a hair so that I can switch to when I switch to the plastic tip in a minute, I won't overload. Um, Once you know that everything's working, we can go in here. And again, I'm not going to go over some of these basic settings. The trigger is really all about setting the level of the trigger above the noise floor so that you get a reliable trigger. And then you want enough pre-trigger so that you capture the rising and falling part of your force pulse. So that's all there is to do there. Um, these trickier ones, okay, and then actually let's talk about the bandwidth real quick, do the bandwidth check. This is actually a really useful feature in TestLab because it automatically will do a test up to your set bandwidth and then one up to 4 times as high so you can check that there aren't any forces or any modes in the response, lightly damped modes that are showing up. If you have anything strong in this, oops, in this range, that could be picked up by the or could be, you could fail to filter that out with the anti-aliasing filters, and you could run into trouble. Now, how do we set actually, let's do one more hit. Looks like I got a bit of a double hit there. Oh, no, still about the same. There's my measurements there. How do we set the bandwidth? Usually it's easier to do this on a dB scale. So you notice that um, the hammer's effective out until you get down, in this case, to about negative 80 dB or so. That seems like the force is starting to fall off. Um, So that's negative 80 starting at negative 23. So about 60 dB down. So you want your measurement to mostly, measured range of interest to be mostly, in about the first 40 dB or so. So here, 26 to 66 would give us 40. And that gets us out here to about 2000 hertz. If we want the first 6 modes or so, then we'll do just fine with that. So what if that wasn't enough? I can pull the cap off here and we'll do another hit with a hard plastic tip. With that one, I have to hit a lot softer. Um, and we got both hits now. The hard plastic tip falls off quite a bit less. Um, Here I have a little bit of a double hit or something, so you get this scalloping in it. But notice here, we make it out to a little bit higher frequency. We're kind of maintaining amplitude and the lower bandwidth with that tip. Now it turns out the rubber tip I have is pretty hard. A softer rubber tip could go even lower in amplitude, lower in frequency than what we're seeing. But you get the idea that the that we can use the tip to control the roll-off. Actually, let's just be a little bit more specific here. So notice with the hard plastic tip, we get less energy into the structure at low frequencies. So we start at negative 40 dB. But here we've only dropped, at 2000 where we used to be dropping 40, now we've only dropped 20. So quite a bit more effective over a range of frequencies. Let me just update those two plots real quickly because it kept measuring while I was talking and had my measurements. So that was definitely a double hit. You can see how contaminated the spectrum was there. I don't know if you can hear the sound from the structure, but that is another indicator of a double hit. Oh, and I overloaded, but still did reasonably okay, so we'll run with it. So yeah, so here we have negative 34. We drop only 10 dB now over 2000 hertz with my newer hits. And you can see on this lower plot, 40 dB takes us out a little farther where we were down 60 dB before. So we could choose what we want depending on how many modes that we want to get. In this case, we want the first 6 or so modes up to about 2000 hertz. And so it looks like, this might be better. It stays nice and flat over those 2000 hertz, but it's always harder to hit with a harder tip. If we go back to the soft tip, things decay a lot more quickly. We avoid putting energy into modes that we don't want, and we get more energy into the ones we care about. So I'm going to go with that. Okay, next let's talk about windowing. How long, and before we talk about windowing, let's just turn the windows off completely. And I guess the force window we can always leave on. That one's really straightforward. Its only job is to zero out the force signal after a certain amount of time so that if you accidentally bump the hammer after doing a hit, that's not recorded as part of your measurement. So that window we just set to make sure it captures the hit and any double hits. So if we run it again, if I accidentally had actually with this one, I can't really even fake a double hit very well. So I guess I won't try to with this one right now. But we want that to capture any double hits. And other than that, we don't worry about it. The next thing we think about is how long do we need to measure? In vibration theory, we know that if we measure the response out to 8 time constants, that we'll get 2 points in the half power bandwidth in the spectrum for that mode. and that lets us capture the damping of the structure accurately. So, so this measurement, we have a 0.6 second acquisition time. That sets the resolution of our spectrum. And we don't capture the decay very well in this case. So we expect quite a bit of leakage in a measurement like that. Let me backspace here. This is the full measurement. We only really see a lack of leakage if we really zoom in on a mode of interest. So if we want to actually capture the decay, we can up the number of lines. Now the measurement will take 10 seconds, so the resolution will be 1/10 or 1/10 of a hertz. And if we do this measurement, it takes quite a while for the measurement to finish before the screen updates. But when it finally does, we'll see that we have a much higher resolution measurement in the frequency domain. And now the response has really rung down well. And the modes have decayed really well by the end of the measurement, so very little leakage. And we can see here now we have plenty of points to see the half-power bandwidth for this signal. All of this is a lot easier to do in the navigator. So what I've done is loaded in two measurements so that you could compare them. So notice the one with the 0.64 second measurement, the resolution was poor. And if that was our measurement, we might have thought we did okay. But if we look at the half power bandwidth, 422 times 0.707, that'd get us down in this range right here, 28 or so. So you can see that there's only one, we only have about 1 point, maybe, I guess it looks like we might have 2 points in the half power bandwidth. In contrast, if we take the high resolution measurement, this one's 1100, so we'll go down to about 0.75 or so. So now you can see several points within the half power bandwidth there. We've resolved the peak well. We'd expect that to be an accurate measurement. Now, as I've talked about resolution, though, I've given the impression that we're going to use the half power bandwidth or this kind of log peak picking approach with half power bandwidth to get the damping. Does all of this hold if we can use a modern tool like curve fitting to get the damping? Let's take a look at that. So over in MATLAB here, I have a curve fit on one with a 10-second window and a curve fit on one with a 0.64-second window. And we can look at this two ways. The problem is always worst with the lightest damped, typically lowest frequency modes. So if we zoom in down on this mode, you can see that there is a little bit of error. The red is the error in the fit. But, it actually looks like it's pretty good. It looks like we did reasonably well. Oops. I forget that MATLAB doesn't let you do backspace to zoom out. Okay, so it looks like things are pretty much okay, but there is definitely a little bit of residual there. If we compare that with the measurement at the much higher resolution, now the residual has dropped a lot. It looks like we're able to fit these first four modes at least really well. I should have also pointed out the Nyquist plot's a really useful tool in this regard, though it can be tricky to match peaks. But basically this one right here is the first mode, and then this one right here is the second mode. The Nyquist plot should make a circle for a mode. So if we don't sample that circle well enough, basically the number of points beyond the center of the circle is the number in the half power bandwidth. And so you can really see if there's a mode that's not well resolved. If we come over here, we can see in the Nyquist plot, all of the circles are really well resolved. And that same thing then holds if we go and we zoom in on a mode. There's still error in the curve fit at the resonance. There's still some amount of leakage getting through or noise of some kind. But now we can see we have plenty of points to define the resonant peak there. What's the downside? The downside to this measurement, well, it took 10 times longer, more than 10 times longer, but also we go to the higher modes and things get noisier. And that kind of makes sense if we go back to TestLab here, because this higher frequency mode decays really quickly. And then at its frequency, we just record noise for a really long time after that mode is already gone. So we'd expect that some of those higher modes will get noisier as we use this overly fine resolution. Actually, maybe it was this one that we got really noisy on. So we usually want to strike a balance between those two. So a good way to strike a balance is we can go back, kind of to something in between, and then we can use an exponential window to force the signal to decay more quickly. So now we have a 1 second measurement. The signal does decay a little bit in the measurement, so we haven't left everything to the window, but we'll force it to decay even faster. Let's even go kind of extreme with a 1% exponential window. And now what happens is now we see the peak is better resolved because what we've done is we basically added damping to the system. So it's as if we're measuring from a system that does decay in a fraction of the time of the original system. So that will cause all of the modes to be more heavily damped. So that's good, and it lets us get our measurements done more quickly. It could be a problem if we want to measure some of these higher frequency modes that already are heavily damped. They may no longer even stand out in the measurements if we put on too much damping. But actually, these modes are minimally affected because they already decayed very quickly. The amount of damping we added did not really affect them a lot. We can see this over in the navigator. So if we took if we took our 0.46 measurement, the one that didn't have enough resolution, and now we apply the exponential window, we've basically added a lot of damping to that. And the resolution is now good in terms of the damping that we have, but our dynamic amplification has changed a lot. If we zoom out, the same happens for all the modes. Again, less at the higher modes, which we can talk about later. But yeah, basically we've increased the damping. Now we have no more frequency resolution issues, and we get a good measurement. So this can be a good way to go. It kind of gives us the advantages of a cleaner, more highly damped measurement, one that we can curve fit really well with minimal errors while making the test faster. This will also tend to make mode shape estimates more accurate. So that can be a good approach. And just in summary, what we ended up doing was using an exponential window that forced our signal to decay in the way that an ideal measurement would, but trying not to overdo it. We at least did take, plenty of cycles, even of the lowest mode, so that we could see it decay. All right, so that's everything. With that, you'd be ready to measure. So we could go and take a measurement. This one is, we'll give that measurement a name. Here I'm not doing any averaging. We're ready to go. We can do a hit. I like to have things set more or less like this, but usually I'd like to see a bit of a zoom in on the force so I can see if I put a good hit in. I want to see the force spectrum here to make sure nothing funny happens. And then we can see our frequency responses and see how things are coming. Okay, that's everything for today. We will see you next time.